here we're depicting a series of wave fronts. Just think of waves coming into the shore of the ocean. But these could be wave fronts, they could be electromagnetic waves, they could be sound waves, they could be any kind of waves, where we have wave fronts progressing at even intervals. And what you can think of is each of these lines will correspond to a peak of the wave. So these waves are coming in this direction. The direction of propagation of the wave is going to be perpendicular to the wave fronts. Now, what happens, we move from one medium to another so that the waves slow down in the second medium. So we're assuming that the waves are slowing down. So we have a certain distance between the wave fronts in this medium and a reduced distance between the wave fronts in the second medium. The result is that the disturbance created by this wave front will propagate only this far into the new medium, while this point on the wave front will propagate the full distance between the wave fronts out here. It'll propagate by a whole wavelength here, but this will be the wavelength in the new medium. The peak of the wave here will occur at the same time as the peak of the wave here, and we'll have a wave front along this green line, which, because of this distance, because of the fact that this distance is shorter than this, is going to be at a different angle than this one. It's going to be at a lesser slope if we regard the slope relative to an axis along the interface between the two medium. So that the direction of propagation in the new medium is going to be perpendicular to the new wave front, and it's not going to be at the same angle it's not going to be in the same direction as the direction of propagation that was parallel, or that was perpendicular to the fronts in the old medium. Now we look at this from a little bigger perspective. Again, here's the direction of propagation, which is perpendicular to the wave fronts in this medium, and we have wave fronts in the second medium that are at a different angle and a direction of propagation perpendicular to those wave fronts. So that we have an incident angle. Oh, well, let's back up a second. We're going to let this dotted line represent the normal direction, the direction perpendicular to the interface between the two medium. So that we have a wave propagating at some direction, theta sub I, incident angle, theta sub I measured between the direction of propagation and the normal, and an angle theta sub R, this angle here, between the normal and the direction of the wave propagated in the new medium. Now, let's go a little deeper into propagation velocity. Okay, we're going to let C be the propagation velocity in a vacuum, and we're going to think right now in terms of a sound wave. I'm sorry, an electromagnetic wave, a light beam, say. Okay, so C stands for the propagation velocity of an electromagnetic wave in a vacuum. Then the propagation velocity in this first medium is going to be C over some number n1. Any medium is going to tend to reduce the speed of propagation of the wave, so that n1 is the factor by which the speed of propagation is reduced from its free velocity in a vacuum to the velocity in whatever the medium is here. And then in the second medium, propagation velocity will be C over n2. C2 equals C over n2, where n1 and n2 are again the numbers that you divide into C to get the velocity in the given medium. These are called indices of refraction. So this n1 here is the index of refraction in the first medium, N2, the index of refraction in the second medium. The greater the index of refraction, the more slowly the beam travels in that medium. So the picture we've got here is where the propagation in the second medium is slower than the propagation in the first medium. Okay, so that N2 is going to be greater than N1. Bigger N2 bigger than N1 means that C2 is going to be smaller than C1, since the index of refraction occurs in the denominator. Okay, with those definitions, we can state Snell's law. Now, I can do a little bit of trigonometry with this picture. I'm not going to do that because we're in a situation where we've got to gloss over a few things, but you can read it in your book. Snell's law dictates that the sine of theta sub r, the refracted angle, divided by the sine of theta sub I, the incident angle, is equal to N1 over N2. N1 being the index of refraction that goes along with the second medium, so N1 sort of corresponds to the incident. So you see that N1's in the numerator and the incident angle in the denominator, and N2 corresponds to the medium in which the propagated wave, or the refracted wave, travels, so that N2 is in the opposite part of the fraction from theta sub r.